Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to describe pulleys in the context of what they do, what you can use them for, and how you will see them in a typical physics class. So we're going to start our discussion here with this left-hand side. And in my picture, this is intended to be a pulley. My apologies, it's kind of large relative to the objects in that. But we're going to imagine here that this is a light, well-working pulley, meaning that bearing there is oiled and it's working, this pulley's in good working order. Hanging from this pulley are a couple of objects here. We've got this blue object on one side, this red on the other. And for the sake of discussion here, we're going to imagine that this blue one we know to be 100 pounds. Now, also for the sake of discussion, this is my symbol for observing here. That's like an eyeball. We're going to imagine we observe that the velocity of both masses is zero and not changing in this problem, zero velocities. So we're going to think about the pulley, its role, and kind of what's going on here. So the first thing I'd like to point out here is this. We're going to draw a free body of that blue object. So if we draw a free body of this object, and again, free bodies should always be kind of standalone pictures. It's not really good form to draw force vectors here. This is really kind of a picture that describes our problem. The weight of this object acts down. And that weight, which is the force of gravity, we know to be 100 pounds in this problem. Now, because we're observing this thing's not accelerating down, there's got to be an upward force, and hopefully it's fairly obvious where that's coming from. That's coming from the string or rope here attached to this. So that's creating an upward force, which I'm going to typically call it T for tension. And it's pretty common in physics to call forces like that tensions. And there's nothing else in contact with this. So those would be the two forces. Now, the net force has to be zero. So sum of all forces equal to zero. Doesn't matter which way called positive. I'm just going to skip to the results that everybody probably already realizes. That tension force must be 100 pounds. Otherwise, this thing would be accelerating. Now, another common question that I ask people is, right, if the blue guy here is 100 pounds, what would the red guy have to be in order for this system to be balanced and not accelerate? Remember, assuming that this is well oiled. If the red guy were, say, 105 pounds, this should start accelerating down, this should start rotating this way, this would start accelerating up. And if the red guy were like 95 pounds, the reverse of that would be true. So just about everybody comes to the conclusion that in this example, this would have to be 100 pounds. And if we draw a free body now of the red mass, sorry about that. All right, copy, paste. Put this over here. Get rid of some of that stuff I don't really need. You'll see there. Okay. So we would have a 100-pound force vector down. And then a rope pulling up with some sort of force that we would typically call a tension. And it's pretty easy to show that tension would have to equal 100 pounds. So kind of a long-winded way to get here, but if we think about what did the pulley do here, and the answer basically is it changed the force direction. Or even maybe a better way to say it, the pulley did effectively almost nothing in this problem. The main point I wanted to make is that these ropes have the same tension value. So this is a single rope, string, chain, whatever you want to say, down to here. And there is only one tension, T. And as long as the pulley is well oiled, somebody's been doing their job and oiled that tension would be good on both sides, here or here. So really, what does the tension do? Basically changes the direction of the forces. Now, what do I mean by that? Well, if I wanted to, Imagine the rope came down something like this instead of straight down. And again, we ask ourselves, what would we expect the tension to be? And the answer is still 100 pounds. That 100 pounds would have to be good here, 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 anywhere along the rope. And the fact of this rope changing an angle doesn't change that in any way, shape, or form. Ask yourself this. It's a thought experiment. A couple more here. If I were to take this rope and connect it to a scale right here, and then connect it to a wall or something like that, ask yourself, what should that read? And the answer is, again, 100 pounds. So moral of the story here, when you're dealing with these tensions, I'm sorry, this is getting a little long for this short point, is that you kind of look at each individual rope. In this case, this would be this one in red. And you generally assume the tension is the same everywhere along that rope. And that would be true if we're talking about specifically a static problem and the pulleys well-oiled and stuff like that. Now, if we take a look at the one on the right here, I've got a slightly different circumstance here. And I'm going to just get rid of this now. Bring this one over. All right, so now, imagine we got this 400-pound object that we want to lift. And this has a two-pulley system now, tied like, attached like so. And we're going to imagine this is one string. Follow it, follow it, follow it all the way to here. And we're going to talk about, well, how much force do we have to apply this way? In other words, what is the tension here to support at least this 400-pound object? So I'm going to go through this and talk about how to analyze it. And again, typically we assume things like well-oiled bearing here and here. So this thing's in pretty good working order. That's actually part of this equal tension assumption. Again, that's one rope. And the way you analyze pulleys is just with good free body diagrams. So what I'm going to do here is draw a free body of this object. Again, a free body really should be a picture kind of standalone. It's not really good physics to start putting force vectors here. This is a picture of what our problem is. Now I'm going to start putting force vectors on. So pretty significant weight for this object. So we have a 400-pound force acting down. And again, here's the kicker here. If we define our system like this, which is what I've done, you notice that rope crosses it twice, once here and once here. And there's a force vector for each one of those. So we're going to put a tension up for where that rope crosses that boundary. And here's another spot right here where the rope crosses that boundary, creating another tension up. Now these forces are not perfectly vertical, but I'm going to just assume they are. They're approximately vertical for the simplicity of our problem. We're going to also assume that that is a light pulley, especially compared to the 400 pounds, and we're going to ignore its weight. Any forces, having to do with this are internal to the way I define my system. Then we're going to write our force equation here. Sum of all forces is equal to 0 if this is static. This was not intended to be an acceleration problem. Doesn't really matter. Let's do down positive for kicks. Then we would have plus 400 pounds down minus t for one of these. Minus t for one of these. Another one. And then equals 0. And I'm just going to skip right to the nitty-gritty here. If you solve that for pt, you're going to get 200 pounds. Now this example more demonstrates why would we want to use pulleys here? Well, notice that we're able to lift a 400-pound force with only a 200-pound tension. And again, that 200 pounds is good anywhere on this rope, assuming the pulleys are well oiled and whatnot, including here. So, meaning we would only have to pull on that rope with a force of 200 pounds. So, what we've gotten is an advantage here. We can lift a 400-pound object with a 200-pound force. And that's kind of the idea of a pulley system, to produce what's called a mechanical advantage here. And I'll make other videos about mechanical advantages. It might seem like magic, but I would like to point this out. Yes, the 200-pound force here will keep static, or let's say lift a 400-pound object. But there's a little bit of a give as well. If we wanted to lift that object, say 2 feet, we would have to pull on this rope in this case and make it move 4 feet. So, and that's just a consequence of how physics works. And typically when you have a higher mechanical advantage, when you can, say lift a 500-pound force with a 100-pound force, right? If you want to actually lift it, you'll have to move it 5 times as far. There's always gives and takes in physics, and again, I'll make more videos about that. So before I go here with this video is getting kind of long, I just want to bring up one more example picture here having to do with analyzing pulleys. Okay, I did that. All right, so I'm going to talk about this system, these systems here, which were drawn by somebody else. I'm going to take a moment and give them credit, whoever did it, and talk about, how would we analyze these? So analyzing the pulleys, it's all about the free body diagrams. In each case, this question is asking, what is the tension? What is the tension? What is the tension? So it's all about how to draw free bodies. And if we were to draw a free body here and define our system like this, in this case, you would have a single force down, the weight of this object. And then the rope here crosses twice, once, two. So you would have 2 tensions acting up. If we assume a pretty light pulley, which I imagine the author of this did, we'll just leave that out. All right. Case 2 here. Now, when we look at the second case, there are 2 different ropes. Look at green. I'm going to leave these color coded here. Right? There's a green, and now the other one in blue. Let's tie it here. So this one's going to have 2 different tensions, and the one they're asking for is this one. So I probably would start this with a free body, let's say this, which would have a single weight down and a pair of tensions up. But again, those are the blue tensions. And then a free body of this pulley, which would have, if you look right here, a single blue force vector down for where that rope crosses that boundary there, and a pair of green tensions up. And that will allow you, between the 2 free bodies, to get this. Okay, third one, I'd start with, identify how many strings we're dealing with. Here, let me do that. Look at this. That is a single rope right there. So you're going to have some sort of tension associated with that. I'm going to call it the green tension. There's another one. Specifically a different rope here. I'm going to call that blue tension. And we'll use this pink here. And then this pink guy along here. So let's call that a third tension. So I did them by color, but really you should do probably something like T1, T2, and T3. Color coding variables generally won't, I don't want anybody doing that with their instructors out in classes anymore, put subscripts on your tensions. But all right, let's go through now and talk about, again, how to work these things. Yeah, let's use, what should we use here? We're going to use this yellow here for defining our system. So define your system like this. You'll have a single force vector labeled W down, and a pair of tensions that I've got labeled as T1 up. Write your force equation, assuming these are light pulleys. Then you draw a free body of this pulley, which will have the green tension acting down and a pair of blues acting up. Okay. That should allow you to get tension 2 here, and then you draw this system right here. And that third pulley 2 of the tension 3s acting up and the blue T2 acting down. So anyway, that should be enough here. Plenty long video here on tensions. I hope that this gives most people, or I'm sorry, on pulleys. I hope anybody watching this enjoyed it and has a little better idea of how to analyze pulleys. Have a great day.